Good noon to one and all. Let us wait for few. Yeah, let us wait for few more minutes.
All right. Thank you.
Yeah. So let us start the session. Good afternoon to one and all present in this meeting. Today, this is the second session of day 2 on Atal FDP on 3D printing and design. For this session, we have Dr. D. Kesavan, Assistant Professor, Department of Mechanical Engineering, IIT Palakkad. First of all, I thank Kesavan for accepting our invitation and going to deliver the talk on mechanical testing and characteristics of metal additive manufacturing. I am very happy to introduce Dr. Kesavan to the audience. He received his PhD in Metallurgy and Material Engineering from IIT Madras, Chennai, and received his master degree from Anna University, Chennai. He is also a recipient of prestigious Sudarshan Bhatt Memorial Prize Award, Institution Silver Medal for the best thesis in PhD in Metallurgical and Materials Engineering, IIT Madras, in the year 2012. He has published more than 20 research articles in reputed journals and conferences. Also, he has got 3 patents for his credit. After completing his master degree, he has worked as technical assistant in L&T Hyderabad, and then he moved to IIT Madras for full-time research. He worked there as senior research fellow. Then he joined to National Bearings in the R&D department, tribology section. Then he moved to GE Global Research, Aero and Thermal and Mechanical System, where he worked as a research engineer and elevated to lead engineer. Now he is working as a assistant professor in Department of Mechanical Engineering, IIT Palakkad. His research interests include surface engineering, welding technology, industrial tribology, and additive manufacturing. I welcome Dr. Kesavan to take over the session. Please. Thank you.
Thank you, sir, for the nice introduction. Am I audible to all of you?
Yes. You are
okay.
audible.
Yeah. So let me share my screen. I believe my screen is visible to all of you.
It's loading. Yeah, I can able to see your screen.
Okay.
Yeah.
So again, so thanks for I would like to thank the organizer for introducing me and inviting me for this talk. So I'm happy to be here in the part of this presentation. For the next 1 hour or maybe slightly more, 1.5 hours, I'll be briefly discussing with all of you on these two major aspects: additive manufacturing and mechanical properties of additive manufacturing components. In general, the mechanical properties that are required for AM components to be get certified or to get qualified. So in additive manufacturing, so I'll be briefly discussing about the history of additive manufacturing, why additive manufacturing is important, and its advantages and disadvantages, under what circumstances one should choose the additive manufacturing process for the requirements. Then later, the second of my presentations, I will focus briefly about the testing requirements. That includes tensile testing, fatigue, and harness testing. So this is a brief about my presentation. To start with, again, so I may be repeating, since I'm presenting as a fifth speaker, I may be repeating some of the terms and some of the titles and the definitions. Please bear with me. So I will be using this just for the sake of continuation. Kindly excuse me. When it comes to additive manufacturing is classified under non-traditional manufacturing, as all of you know, and you also aware that under what circumstance we switch from traditional to non-traditional manufacturing process. So additive manufacturing is assumed or considered under the non-traditional manufacturing processes. If you look at the conventional and unconventional or non-traditional manufacturing process, this is the major difference. If I take one specific case, that is the machining, conventional machining with additive manufacturing. So we also call this as a subtractive versus additive manufacturing processes. So the major difference one can see with the additive manufacturing process is that the amount of waste material we are going to generate by making or by this adopting the process is very, very limited, whereas in the conventional, which is subtractive, so the amount of wastage material is very high. Apart from that, you can also see that with additive manufacturing, there is a high material utilization, as I just mentioned, high level of automation, so which is not possible with conventional manufacturing processes, and complex shapes. Any kind of complex shapes can be manufactured. If you look at the disadvantages, low throughput, so which means the amount of component produced or manufactured or printed per hour is very, very minimum when compared to the conventional, and low accuracy. So low accuracy, that depends the intrication or the complexity of the component, and very importantly, additive manufacturing component will not be able to produce super finished components like what you get with the conventional. So you all the time you end up with a rough surface. So we call it as a low surface integrity. So these are some disadvantages we have with additive manufacturing. On other side, with conventional or subtractive manufacturing, so complex shapes are difficult. It requires the fixtures, the tools, and low material utilization. This all we have as a negative. When it comes to positives or advantages, high throughput, high accuracy, and high surface integrity. So in the recent days, you can see there are many suppliers or the competitors are they are available in the market to make the hybrid of they basically combine the advantages of both additive manufacturing as well as CNC, and they introduce the new machine that's called hybrid machines. It does both, so that whatever the problems that are associated with the both can be addressed with the hybrid machines. So I'll give the brief history about the additive manufacturing, and so before that, the definition, I'm not going to get into much detail about it because you already would have listened or studied about it. But when it comes to the 3D printing, at this point of time, and considering the industrial scenario, so there are actually several disruptive technologies available. When it comes to industry, there are majorly 12 potential economically disruptive technologies are available. Say, for example, you take mobile internet. It is one of the disruptive technology, the energy storage, cloud technology. So like you can see, there are several such technologies are classified as a potential economically disruptive technologies. So in that, you see 3D printing also classified in that. So which means the disruptive, the term is like something which is completely changed our day-to-day life or our thought process. For example, take mobile phone. So some 15-20 years before or 10 years before, we did not think of going and being in a queue in banks, right? It's to for cash deposition or withdrawal. Now we don't have to do that. So that's called actually disruptive. So similarly, we can think in 3D printing point, 3D printing or additive manufacturing as well. So it has changed now industry scenario of manufacturing. So to know more about, so let us understand the brief history of additive manufacturing. You can see the first patent was published almost in 1860. So basically they used photo sculpture method to recreate the pictures in 3D. So they used basically wax. So like that you can see there are several such patents published later 1890, then 1951, so like that. But a very important patent that came in the year 1979. So there's patent from US. So this is the earliest description of powder laser sintering. So now currently you see the additive manufacturing. Mostly, you can see the plastics, making of plastic based material by using the additive manufacturing, like tabletop, which you can find it with 20,000 rupees from, let's say, some 10 lakh rupees. But on other side, to print a metallic component, you see the major material used in industry is powder based, or it's called powder laser sintering or powder laser melting process. So that was introduced in the year 1979, but they did not commercialize. So later it got commercialized in the later 80s, and in 1980s it came up with a major advancement. So, and that is because of the CAD, and that is because of the computer evolutions and several associated softwares development and other related things. So now you see today prototyping, proof of concept, and all these things has been changed with the term, the new term called additive manufacturing. So in the year 90s and the 2000s, we used to study all these things like prototyping, proof of concepts, all those things. Now we put everything under the umbrella of additive manufacturing. You see, this is the first. This is the what you are seeing is the first patent, which is patented in 1892. So basically, they used wax to make 3D component. So later what you're seeing on the right side is the powder based patent, which was published in the year 1981. Now you see there are several players available in the industries basically to work on additive manufacturing, like Stratasys, Cubital, Helices, TTM, Soligen, and EOS. There are several other manufacturers available. And if you see, this is how actually it has evolved. So it started from rapid prototyping, and currently what you are seeing, it is mature to the level wherein we can even actually print the organ components, so human organ components. So we are in that level now, and all these things are possible. That is because of computers. You can think anyway. The first patent was published long before, maybe 100 years before, but we are all talking about additive manufacturing at this point of time. That is because of these reasons. Computers, because computers has reached almost its to all the levels, and the availability of softwares like CAD/CAM. CAD/CAM came in the year in industries in the 80s, and improved automation and component technology. Growing library of printable materials. Earlier, it was very difficult to print all the materials. Now you see almost all the materials that can be printed. So if you know the physical metallurgy well, so you should be able to actually make any material printable. For example, copper and brass. So people used to find it very difficult to melt the material to make a component by using 3D metal printing. Now you see there are several players. They make 3D printed components by using copper. So, and investment, and very importantly, freedom to operate the patents. So once the patent is filed, so it basically restricts the other competitors to make the component. So now it is, but it has its own life or time. So now actually we have freedom to operate those patents, which was patented like 15 years or 20 years before. So now the additive manufacturing has grown up because of these reasons. And at the same time, we should also understand what are the unique capabilities of additive manufacturing. So one is, of course, hierarchical complexity, so which you cannot think of manufacturing by conventional process. So for example, what you are seeing on the bottom left is the impeller. So see, to improve its efficiency, so basically one should control its heat transfer capability. You see here at the core, they introduced some kind of fins. So by introducing this, they improved the efficiency of the component. So this is called hierarchical complexity. So as you go from surface to core, so the complexity is increasing or varying. Similarly, if you see the other components, it has hierarchical complexity. On the right hand side, what you are seeing is it is the die component, wherein the conventional cooling channels are made by using additive manufacturing. This component is completely printed by using additive manufacturing. You cannot think of making this channels manufacturing easily by conventional process. So similarly, the other components. So wherever you see there is a material hierarchical complexity, material and shape complexity, functional complexity. So then actually additive manufacturing comes into picture, because these things cannot be manufactured by using conventional process that easily. So the definition of additive manufacturing, I believe you all know that it is a process. Additive manufacturing is a new process of joining materials to make objects from 3D model data, usually layer upon layer, as opposed to subtractive manufacturing methodologies. This is the definition as per ASTM. So here what it says, you have to have the CAD model. From CAD model, you complete your component. Basically, you are from CAD, you are getting actual component by creating layer by layer material. So in that case, if you see any component, 3D printed component, I can see there is a layers. You see that this is the component actually printed by layers. You can find that this is the layer thickness is 60 micron and the layer width is about 120 micron. So now you repeat this 60 micron and 120 micron in all three directions. So you end up with this component. So we call this as a additive manufacturing. Similarly, if you look at the welding process, so I believe you all know very familiar about the welding. So let's say once a welding is done, if you take the cross section, you also end up seeing a similar kind of patterns, like what you see on the right bottom. So this also looks similar, and we don't call welding as an additive manufacturing process because it is not satisfying this definition. So here in welding, we don't use the CAD, so we don't actually print or make the component by using the 3D model. So though it looks similar, the welding process, we don't call it as a additive manufacturing, but we call this as a fabrication process. So welding process is a fabrication process. It's not even actually classified under manufacturing. It is classified under the fabrication process. Now, how the CAD model is printed. So maybe I can give the brief about it. Once the CAD model is generated, so basically, you need to optimize. So there are several softwares available to optimize. When I say optimize, there are several optimization available. Example, shape optimization, size optimization, surface optimizations, and several other optimizations. Those who work on design and structures. So you all will be knowing about it. So you have to do the optimization. Basically, optimization is done to minimize the amount of material on the cross section to get the exact requirement. Once the optimization is done, you convert that into STL file. So STL file is generally it's called a stereolithography file or standard tessellation file, but mostly used term is stereolithography file. So you convert that into STL file. STL file is nothing but actually you are creating the facets on all the surfaces. Then you slice. Right, slice as per the layer thickness, or you can slice, as per your convenient or the machine specification. Once the slicing is done, so basically you have now different layers. You start with the layer n plus 1, n plus 2, n plus 3, like that. You have different layers. So what important information you will get after slicing is that you need to get the slice G codes. So basically, you have the hatching. So for example, hatching for the nth layer is not same for the hatching for n plus 1 layer. So hatching meanings, say for example, here you have the arrow mark. So this is the arrow mark that should be followed by the nozzle, right? So basically what information you need to get here is X, Y coordinates. So to get this XY, so basically you are doing the slicing. So the XY, to get the XY coordinates, once if you know the XY coordinates, basically you know the G codes, right? So all this process is done to get the G codes. Once if you know the G codes, you can feed that into the machine and you can actually control the process to get the 3D component. So you should also know the basic difference between additive manufacturing and 3D printing. So the only difference is that when it comes to 3D printing, basically you will be using the nozzles. So nozzles or torch or whatever you call the element which is used to melt the material. Unless otherwise, you can call that as a additive manufacturing. Right? This is a basic difference between additive manufacturing and 3D printing. When it comes to classification, so there are major additive manufacturing process classified into 7 major groups. So you can see here material extrusion, powder bed fusion, vat polymerization, material jetting, binder jetting, sheet lamination, and direct energy deposition. This is how it is classified. To make it simpler or to understand this simpler, one can also classify this based on the energy input. All right, to start with the low energy to high energy. Example, vat polymerization process is the technique which requires very low heat to make the component. So of course, this is used to make polymers or plastic components. As you increase or as you move on from plastics to other materials, for example, alloys or metals, of course, you need to give more amount of energy input to the material to melt it. Example like welding. So we cannot use low energy heat input to melt the material in welding. Similarly, additive manufacturing also more or less in the same concept like welding. So here, as you go on with different materials or metallic materials, you need to supply higher energy. For example, if you are using powder bed fusion, wherein your input material is in form of powders, and that powders can be melted by using either laser or plasma or electron beam, like that. Those are the sources. And you have another process which is called a lens process that comes under the direct energy deposition. Here you'll be using a laser, so within a very high heat input. So this is how the additive manufacturing process are classified based on the energy. Now, very important question: why additive manufacturing? So I'll give some examples. So this is the one what you are seeing here, which is the seat buckle, which is normally used in airplanes. So you would have seen all this. So this is the conventional process, traditional design. On the right hand side, what you can see, this is the new design adopted as per the additive manufacturing process. So you see now, with the new design, so almost the weight has been reduced 50%. Almost half of the weight has been reduced. So if you consider in total, almost it reduced the reduction weight of 72.5 kg, which can accommodate one passenger more into the flight. Okay, so this is one such example. And similarly, we can give other examples like jet engine bracket. So here you can see there is almost 84% reduction in weight. You see, the basic difference with the conventional design and optimized design, only the difference is the complexity. So that complexity cannot be taken care by conventional process. So with additive manufacturing, it becomes easy. So by doing so, we are not compromising with the functional requirement. Here, the functional requirement, it has to withstand the required load or stress. That part is not compromised. Without compromising that, there is a good amount of material has been reduced, so that the weight of the aircraft or whatever the component has been reduced considerably. So this is the another example. So I would like to briefly run one video to show how it is benefiting in aircraft industries. Let me know if you are able to listen the video. Are you able to listen the video?
No, still in presentation mode.
When I play, I'm able to listen the video. So are you able to?
I think you need to share your screen, entire desktop. Then only it will come.
Okay, so then I need to drop this, right?
Yeah. Now it is coming.
Oh, it is coming now.
Yeah, you play once again.
Is it coming?
Just wait, it is. I think it is loading.
Hey, I'm Allie.
Hey, Ali, I'm Gordy. Nice to meet you.
Can you please confirm? I'm able to listen the audio video both.
Yeah.
Are you able to listen?
Yes.
Okay.
This place is huge. What is happening?
Yeah, this is essentially the Burning Man for private pilots.
Okay, so all the plane nerds are here.
Absolutely.
Right?
People everywhere. Yeah.
I can't wait to see some stuff. Let's go look.
Yeah, let's do that.
Okay.
Cool. Go this way.
This is crazy. I have never seen anything
That's right.
of this scope. I mean, how many planes are...
This is an engine that was originally designed back in the 1960s. We've just continuously
Sorry, I'm checking it again. So you are able to listen to it, right?
Yeah.
improved it over the last 50 plus years. Just keeps getting better and better and better. And it's really a fantastic engine up to about 850 horsepower.
What came next after that?
So let's go over to the next one, the next link in the chain.
Ooh, what is this?
So this is the T700. This was designed back in the 1980s. You can see it's more complex. It's a more powerful engine than the last one we looked at. This is really used primarily for helicopters like the Apache and the Black Hawk. This is basically state of the art today. Now let's go look at what we're going to do tomorrow. Future. All right, so this is the advanced turboprop. And what we've done here is we've taken all of the best technology and learnings from those last two engines, plus everything we've learned on the large commercial engines, and we put it into this.
So what's different about this engine?
Two things that really make this engine different, and that's one, there's extensive use of additive manufacturing.
Oh, okay.
And then the other thing is this has a digital engine control.
What is digital engine control?
The planes that we saw on our ride, basically they all have a hydromechanical control, which means the pilot has to make a decision on everything. So they're independently controlling the propeller, they're controlling the engine.
Right.
So what this does is it simplifies all that into an electronic control, and that frees up the pilot to think about other things. So they can really fly the aircraft instead of flying the engine.
Is this GE's first turboprop engine with additive manufacturing?
It's really the world's first engine with extensive use of additive. Basically, we took 855 parts that would normally exist if we did it conventionally and condensed that down to just 12 parts. You know, parts that are large, complex assemblies that have to have people assemble those things together. And those parts add weight, they wear out, and they create leakage paths, which robs the performance and efficiency of the engine. So the end result that you have here is a combination of technologies that we've really never used on small engines before.
What do these parts look like?
Okay, so we have some over in the cabinet over here if you want to go take a look.
Yeah, let me see.
So this is a fuel heater. So fuel goes in here, and engine oil goes in here and heats the fuel.
Now this is one part.
This is one part, that's right.
How many parts would you usually?
So normally this would be about 300.
300 parts.
That's right.
Is it lightweight?
It is, so it's about half the weight it would normally be.
So this is one part.
One part.
That.
Yeah, so the takeaway is I actually have other videos, but I'm not able to run considering the time. So the takeaway is with additive manufacturing, so the part consolidation has play a very important role. So in this video, I think you would have listened to that the almost like 850 plus parts have been consolidated into 12 parts. So those many number of parts minimized into 12 parts, and particularly the fuel pump, which was earlier they used to make almost like 200 or 300 plus parts, now consolidated into one part. So that is the major advantage for additive manufacturing. That's the reason you see almost like many of these components are engines now they are not trying to replace with the additive manufacturing with the conventionally manufactured components. So you can find more videos in ge.com. Right. So apart from that, so you can also see, these components and process being used in biomedical applications, and you can also see in other applications. For example, in Aston Martin's DB7 Skyfall movie, they printed this car by using additive manufacturing, and they crashed it. That they have done basically to record the audio of the crashing sound. And similarly, you can see the 3D printed house and also the Nike 3D printed shoes. If you look at, if you see our size, maybe we'll be choosing either 8 or 7 or 9, but our size may be in between, maybe 7.5 or 8.5, like that. So Nike, they use 3D printing technology to print the size of the shoe to accommodate our exact size, and more usage in biomedical applications also in place now. So but this all the advantages, but on the other side it has also some disadvantages. So as I said here, part consolidation. So this is the fuel nozzle that is used in GE engines. So earlier they used to make this component with the 18 components. Now that has reduced into one, and 18 number of components reduced to one, like what you're seeing on the bottom left. So see, this is 3D printed LEAP engine fuel nozzle, which is made of a single part. So there is no assembly required. So which means any defects associated with the assembly can be eliminated by adopting additive manufacturing process. And this also give advantages of a lighter weight, 25% reduction in weight, and higher durability. But the problem with these materials or additive component is the major is it cannot take the dynamic load. So far, whatever the component that you have seen, they mostly used in the place where it can take only the static loading. When it comes to dynamic loading, it cannot actually stand the fatigue load. So that's the problem. So like what you're seeing on the right hand side, you see as the crack increases, the stress required, or the number of cycles that takes the cracked specimen, particularly made with additive manufacturing, has decreased drastically. I'll discuss more about this in the later part. Now we cannot choose additive manufacturing for all the applications required. For example, let's say I have one component. So now the question is, can I replace the component which is conventionally manufactured with the additive manufacturing? So we cannot do to do so. We should also know the advantages and disadvantages of additive manufacturing. Then we should know under what circumstances or under what condition we can actually choose additive manufacturing process. So this all is based on some parameters. I will discuss that in detail. We should also think that additive manufacturing cannot replace the conventional manufacturing process. So conventional manufacturing process has reached to the level or maturity, or we can say that it is a robust manufacturing process. Conventional manufacturing process is the robust manufacturing process, and that cannot be fully replaced with the additive manufacturing. Rather, additive manufacturing can play a complementary role. So if any complex shape you have which you cannot manufacture by conventional, then you can think of additive manufacturing process. So and like I mentioned, part consolidation. Let's say if you are looking for a part consolidation which cannot be possible with the conventional, you can think of additive. So like that, there are some examples. I'm going to discuss that now. So for example, so let's say you have a component. Now you need to actually make or select the process to make the component. Now can I switch from conventional to additive manufacturing? So you can actually think of that. So you cannot make an abrupt transition. Say for example, if you have a component like this component definitely or certainly cannot be manufactured that easily with the conventional process. You need to have at least, you need to have 5-axis or 6-axis milling machine to make this component. If you have a component like this, it meets all the requirements whatever given here. Say for example, it adds value by switching additive manufacturing. It adds value, the cost of manufacturing is decreased, and productivity can be increased, and it sustains for long. Sustainability is what is done today will sustain for future as well. So you can end up getting this component. This is a component printed in our lab at IIT Palakkad. So in this case, you can think of switching from conventional manufacturing process to additive manufacturing. Now I have another component. So this is the bolt component. Now should I actually use the additive manufacturing to to make this bolt. So certainly it is not a good idea to switch or to manufacture this bolt, because so there is, as I said, a conventional manufacturing which is robust available to manufacture these components. Now you can get this for 5 rupees or 10 rupees. So if you fit that into this map, it will not be able to meet any of this requirement. It will not add any value. Cost will go high, productivity will decrease, and technical it cannot sustain for long. So certainly you cannot actually make this component by using additive manufacturing. So then the very important is you need to look for what value that is added by additive manufacturing process, and what are the functional requirement or functional, whether it meets the functionality requirement and manufacturability. So if you see that you are meeting all these three requirements, then you can switch to additive manufacturing process. So there are some examples I can quote here. Again, impellers. So conventionally manufactured impeller is what is shown on the right side, and to improve the efficiency, so people have adapted actually moving to additive manufacturing. By switching this, they found that there is about a 2.5% increase in efficiency for every 100 degrees Celsius improvement in the increase in the temperature in the turbine. So here it really adds the function. So similarly, if you look at the pump housing component, so here you see there is a material advantages. You see the material efficiency with additive manufacturing has improved 67% when compared to the conventional manufacturing processes. So like that, you can find there are several applications are available in the literature or in the industry scenario. So if you look at the scope for additive manufacturing, you see it is increasing progressively. You see the market has increased to the sizable amount, and it is predicted in 2025 to reach almost like 8,800 US million dollars. So it's all in millions. So which means going forward, you can see more industries will actually come into get into these additive manufacturing processes. And particularly if you look at the amount, so in additive manufacturing there are several processes available. If you look at the processes, DMLS or SLS or FDM, they play a very important role, and people are switching or adopting this technology in industries more rapid. And you see here in 2024 it is expected, DMLS or SLS, so both are powder bed fusion technology. They are expecting to grow to very high level, so by 2024. So the takeaway is there is a scope, and industries are switching, or they are getting into additive manufacturing to make their components. And you can also see a lot of PhD thesis and publications in recently it is coming up on additive manufacturing processes. All right. So and other important DFAM concepts, I believe you all actually would have listened from the previous talks. So I'm not going to get into that much detail. But one, we should understand that DFAM is done basically to it is done for minimum material that meets the functional specification, part consolidation, minimum material that meet the manufacturing processes, improved function, optimized material type, and minimal residual stress, optimized build orientation, minimal support structure, and efficient and traceable workflow. So this all the functional, this all the very important aspects one should consider while working on the design for additive manufacturing. So it is nothing but you are preparing your the component so that that can be printed easily and with high efficiency by using additive manufacturing process. So for example, so this is my component, and I know the functional requirement of the component is static and the load is applied at the one end. I'm seeing that conventionally, if I think of, I have to basically make this component by using this plate. I actually need this size, this much size of the plate. So what I'm doing, I've just done some quick FE analysis. I'm seeing how the stresses are getting distributed here. So now I have the option of minimizing the materials. So what I'm doing by optimization technique, I'm removing the material where there is no load sharing is taking place. So I have removed the material. Now finally I ended up making this kind of materials. Now I'm doing stress analysis. So it gives me the same. So wherever those load or stress were not distributed, I removed those materials. Now I can actually use the improved design version for my requirement. So for this, I need to either I can make by using additive manufacturing. If I further make it complex, I can do that as well. So I can make the component further complex so that the further amount of material can be minimized. In that case, I can go for additive manufacturing process since it has now complexity, more complex in the structure. So that's what the design for additive manufacturing. So that meets the functional requirement. You see here, this is a conventional process, and by doing the optimizations, one can reduce the material significantly. So in this case, the bracket has seen to be reduced with almost 79% in mass. So like this, you can see there are several other materials or the components are used in additive manufacturing. And so like this I can give more examples. And the second is part consolidation. This I have already explained. And third is minimum material input. So more the material input, higher the residual stress. So we need to actually think of and reduce or minimize the heat input and the improved function. So if you take the casting process, so what you're seeing here, the conventional cooling, which is used in the dies. So conventional cooling will improve the function. So you can see here the better heat transfer. If you have the better heat transfer function, so the property of the material will be seen uniformly all the cross section, all the three directions. So there is the advantage of using the conventional cooling or conformal cooling. Similarly, in optimized materials and minimum residual stress. So there are several such DFAM techniques available. So what is important here? So I'm going to skip all these things because considering the time constraint. So what is important here is you need to make the material which can be fed easily into the additive manufacturing machine. So it requires a lot of support structure. So you need to design such that you will be having very lesser support structure, and you also orient your component perfectly or to the required orientation, so that you avoid more amount of scaffold material. So for example, so if you want to actually print the component like this, what you're seeing on the bottom left, so you see there is a overhanging. So if you have such overhanging, you cannot print this component without having support structure. So what you're seeing in the blue, they are the support structure, right? So these support structures are waste material. They are also printed by using the same material. In principle, but you will be wasting them. You will be actually destroying them and scrap them at the end. But there are some conditions based on which you need to give the support. Say for example, if the diameter is more than 8 mm, right, you need to give them support, right? And if the inclination is lesser than 40, you need to give them support. If the overhanging, what you're seeing, is considerably larger size, then you need to give them support. So these are all the support structures. So what you are seeing here, but you cannot print the component without having the support structure. That's the reason while design itself, you need to actually think of avoiding such overhanging dimensions. For example, if the hole size is greater than 8 mm, so you will end up with this kind of issues. You try to avoid these dimensions or overhanging also. So you need to have all these things in your mind frame before you design your concept for printing by using additive manufacturing. Like what you're seeing here, so this is how very efficiently printed component by using support structure. As I said here, so this is all the support structure. You see here, it's all the support structure. The support structure will be scrapped later. So finally you end up with this component. So if we don't adopt the design for additive manufacturing, then we end up with adding more amount of such scrap material as a scaffold material. So we should be very careful in designing. So we need to understand what is the design for additive manufacturing in these aspects. For example, if I don't follow, So if I don't follow those conditions, then I end up with this issue. So for example, as I said, if the inclination is less than 40 degree, then I need to give the support. You see, as I decrease the inclination, you see the material is getting actually collapsed. So to avoid this, I need to give the support structure. Same like what you're seeing on the right side. So overhanging. So if it exceeds the limit, then you can find there is a warping. So it won't actually meet the dimensional requirement. So you need to actually account all these things in the picture. So finally, process controls or process parameter also. So how to use or what should be the process parameters, heat input, laser parameters, the powder parameters, the stock parameters, scan strategy, and all those things has to be considered. So under design for additive manufacturing, all these things are processed before you put your component into the AM machine. So this all a very important requirement. You should do that, and you should practice before you are starting your printing. Otherwise, you will be wasting time and money, material, and all aspects. Right. So now we know that. So there are several steps involved. Basically, you start with the idea, then 3D printing and post processing. Most of the people now currently they work on post processing. In post processing, that includes like surface engineering, heat treatment, surface engineering that includes polishing, smoothing, blasting, coloring, grinding, and all those things. Now, most of the literature or publications, what you see now, is mostly focused on post processing only, which includes testing. So, in big picture, if you look at how the additive manufacturing, particularly metal additive manufacturing works, you see here. So you have basically laser or any other heat source, then that interacts with the metal powders, melting is taking place, then there is a melt pull dynamics, then solidification takes place. So finally, based solidification that determines the microstructure, then microstructure that determines the mechanical properties of the material. So there are several aspects or phenomena taking place at the same time. So one have the opportunity of working in all these aspects. Say, for example, if you are very good in heat transfer or CFD, you can actually work on melt pull heat loss or melt pull dynamics. If you are good in CFD, you can work on melt pull dynamics. If you are good in heat transfer, you can work on heat loss and solidification, all this related. If you are good in materials, you can work on microstructural characterization. If you are good in material testing or design, you can actually think of working in finding the mechanical properties of printed components. So it opens a wide space for researchers to work on various areas. So if you are interested in doing or pursuing your PhD or research, so this is a very hot topic. You can actually plan working in these areas. And at IIT Palakkad, we also have facilities available. Please reach us. We'll be happy to help you in this regard. Okay, when it comes to testing requirements, so now whatever the component you process, like I mentioned here, whatever the component you process, so that component will have the microstructure, and the microstructure is purely determined, it's a solidification, right? So how you solidify from high temperature to low temperature, that determines the microstructure. Then the microstructure determines the mechanical properties. So when it comes to mechanical properties, so you need to test as per the standard. So there are several standards now available. So for example, if you take an ASTM standard, so the standard required for or it is drafted for all these 4 conditions. So there are some general standards. It's called general standards, which includes additive manufacturing, terminology, test methods, safety, and all those things. There is a general standard. Then there are some standards available to the specific. It's called application specific. So where it is being used, whether it is being used for aerospace, automotive, medical, or any other applications. Feedstock. Standard feedstock material, standard for feedstock that is specifically focused on material. So what is your input material and how to actually find the quality of input material like powders, wires, and all those things, process and equipment. Similarly, you also have standards for finished AM parts, non-standards like finished, like you're seeing on the right bottom here, finished AM part. That includes post-processing methods, NDE, and several others. So once the component is made as per the standard, this is as per the ASTM standard, ASTM F42. This component has to be tested as per the ASTM standard. So the testing when it comes to testing, so you have mechanical testing. There are several other testing like metrology testing, NDE testing. There are several other testing, but I'm going to focus only on mechanical testing aspects in the next slides. So like I said here, you see here there are several hierarchy. So there are general standard structure, so which is called AM general structure. So here they talk about the terminology, what are the data formats, guides, test methods, safety standards, inspection, all those things. Then the next level of standards are very specific to the parts or equipment or material. It's like let's say if the material or if the process that you use binder jet, right? So then the standard is available specific to that process or that equipment. And if you are using the powders, then there are standards available specific to that metal powders. So this is the second level of standards available. And the third level of standards, it's very specific to the material. Say for example, what if it is a powder, what powder it is. Is it a titanium powder or aluminum powder or iron powder? No, all those things. So like this, there are various level of standards. So you need to adopt these standards. So before you actually start testing your components for its mechanical testing. So we basically perform testings to find its mechanical properties. So when it comes to materials properties, there are several properties available like chemical, mechanical, physical, and dimensional properties. So all these things are very important. Once the component is printed, one has to test for all these properties: chemical, mechanical, physical, and dimensional, which you call metrology. So very important is the mechanical, because once you make this component, you will be designing this component for either to take or withstand the static loading condition or a dynamic loading condition. So you need to know its mechanical properties. So the testing can be done either low room temperature, high temperature, or low temperature. So basically to see whether it can meet the service life. So you use the process additive manufacturing, powder bed fusion process, then that gives the structure which is slightly different, or not slightly, it is entirely different when compared to the conventionally processed component. So it end up new structure, I mean microstructure. You all know that the microstructure is what controls the properties. So this is like all are interconnected. The process determines the structure determines the properties of the materials. When you say the properties, here we are very specific to the mechanical properties, which includes the strength, fatigue, creep, toughness, and all those things. Now, to start with, so there are several testings available. You all very familiar. I'll go through quickly, some of them. So basically, testings are done for static loading condition and also for dynamic loading conditions. So basically, if you look at those components, you can see the components with and without crack. So that is for both static testing as well as for dynamic testing. This is how the test sample. So if it is a simple tension, you see this is the geometry for simple tension. If it is a compression, this is the geometry that is given B. So for hardness, for fatigue, for creep, one can have this kind of standard samples for laboratory testing. So you can also have samples with the crack. Right, some of the testings as per standard, it needs actually crack. You introduce a crack. This is called predetermined crack, and in presence of crack, you see how the component behaves under static loading or dynamic loading conditions. So to start with, tensile testings, this is a very familiar testing processes. Basically used to find its proportional limit or yield limit, maximum tensile, and all other properties. So as per ASTM E8, so you can make the flat sample or the thicker sample, or cylindrical samples. So one can make a component like this. Once the component is made, you subject them into testing by using UTM machine, and you measure what is the force versus elongation with the strain rate in between 10 to the power of -4 to 10 to the power of -2 per second. So you make the standard sample and test it by using this strain rate, and what you are getting is basically true stress and true strain. So engineering stress, engineering strain. So from engineering stress to engineering strain, one can actually convert to true stress and true strain. I'll tell you the advantage of using true stress and true strain in the later slide. So this is how the components are printed. So you have so many strategies. So you can print the component vertically up, you can print the component horizontal, you can print the component at an angle. You can also print the component by using other parameters like an heat input. So for example, you don't have to use 400 watt. So you can use lesser wattage or higher wattage, or you can use various energy density, that is joule per mm cube. How much amount of energy has been spent to melt the unit volume of materials. You can vary. So like this, there are almost like 200 plus parameters available in additive manufacturing or in metal 3D printers. More than 200 parameters available. You use all those parameters and make your components. So once the component is made, by simple tension test, you can find how the properties looks. So always we should be remember that we should compare these components with the baseline. So the baseline is the wrought product. For example, if you take this is the 3D printed component, what is shown on the top right top, it is actually build direction. The testing is done by pulling opposite to or pulling perpendicular to the build direction. So what is seen here is it shows on a higher strength, but ductility is limited. Right, so we should always compare these properties with the baseline. In this case, baseline is wrought. Wrought is what commonly available, so you can compare. So you can quickly conclude that though the process has given or ended up with a higher strength, but the ductility is compromised. So ductility is not improved. It's a low ductility. So now you choose for your application whether you require or this much amount of ductility or you need more. So you can tweak the further parameters and match your requirement. So the important point is always we should compare this with the baseline, which is either a wrought or sometimes cast also. You see here some of the heat treated components. It's actually tested under tensile or static loading conditions, and see as built and heat treated. So sometimes you can see the heat treated samples show the higher amount of strength, but when the strength is increased, and it is normally seen that the ductility is compromised. So ductility is seen to be decreased. So this is what a general trend that can be seen in the additively manufactured samples. And basically by testing all these things, we can get these parameters, which are very common even in the normal specimens. So what do we do? So once if we know the engineering stress strain, by using relations, one can find true stress and true strain also. So sometimes it requires to correct your curve. So basically you see here, so you need to correct it. The correction is needed because the testing is in general done under pure uniaxial condition. So what happens once the necking starts, onset of necking, so the uniaxial will turn into triaxial state of conditions. Once if you have triaxial, then it is no more uniaxial. So to match this with uniaxial, you need to actually correct. So this is the corrected actually curve that is normally seen after necking. So to correct the curve, basically you use this equation, and you can actually, and that equation it includes the dimension of the necking. So once if you have, you can correct. So once you correct this, you will be able to find the exact ultimate strength and fracture strength of the component. So that is possible only with the true stress strain curve. And the next testing, very important testing required, is the fatigue. So fatigue, you all know that the failure of metal or material under fluctuating stress conditions. So if you see there is a small crack in the component, this crack will grow depending upon the alternating stress or mean stress. It can increase. You see with the number of cycles or time, the crack will grow further, and it will, once it is reached the threshold value or critical size, then the further growth will be like unstable. So it can grow rapid, and it lead to the fracture. So basically the component will break into two pieces. If you look at the fatigue, there are two major types of fatigue: plane fatigue and contact fatigue. So plane fatigue, I think what normally you would have seen is plane fatigue, that's a rotating beam bending fatigue, where the stress ratio R is maintained like -1. In normal fatigue, the stress ratio can be varied plus plus or minus minus, or it can vary positive or negative when it comes to contact fatigue. So in the contact fatigue, so rolling contact fatigue, so you see, this is how the normally the bearings or gears and all those components are failing. So these are the other types of fatigue that comes under the contact fatigue and fatigue. So what is important here, that depends your application. If your application requires rotating beam bending fatigue or normal fatigue, you can choose those experiments and you can perform those experiments. So here basically you need to change or look into what is the mean stress, what is the range of stress, stress amplitude, stress ratio, and amplitude ratio. So whether you are maintaining the R value -1 or R value positive or negative, or it is random. So depending upon your stress values, you can choose testing either with a specimen with crack or without crack. You see here on the right hand side, there are some specimens can be tested with the crack, and the left hand side, these are the specimens without crack. So there are some standards available for doing fatigue testing. So you can see this all the ASTM E standard. It's all classified under ASTM E. So, and when you see the approaches, there are three major approaches: stress-based approach, what normally we see or we study. There is a stress-based approach, and a strain-based approach, and fracture mechanics-based approach. The first two approaches are for the solid sample wherein there is no crack, whereas the third approach is for the sample with the crack. And you see this is how the trend, SN curve, and this curve is normally fitted by using Baskin equation, wherein n into sigma is equal to constant, whereas n is the number of cycles and sigma is alternating stress, right, and p is the constant, and this is equal to constant. So this is how one can actually plot the SN curve. But if you look at how the additively manufactured component will fit into this, so most of the AM components will show the inferior behavior. So when I say inferior, the fatigue limit is not seen to be the same as you are seeing with the baseline material or conventionally processed material. For example, you see on the right hand side, this is a wrought annealed specimen fatigue paradigm. If you see the additively manufactured component, they are not actually meeting this. So some of the AM printed components, for example, Ti6 for SLM printed component, which is printed vertically, is seen to have lower fatigue limit. So this is quite natural because the additively manufactured component will have a higher amount of residual stresses in it and a higher amount of disorderness. So you cannot have the same properties in all the directions. So anisotropy in nature, basically. So different properties in different directions, higher amount of stress, and very importantly, the structure is not equiaxed. So it is oriented in one direction with respect to build direction. So all these three reasons are contributing for the lesser strength under static and also under dynamic conditions. So like fatigue. So now whatever the component we process by additive manufacturing, that needs to be tested for fatigue. Now the next question, so should I do sample with notch and without notch? So it requires again applications. So most of the testing standards that requires both fatigue under fatigue with notch, fatigue without notch. So if we have notched specimen, then fatigue limit has been, you can see it has decreased considerably. Again, in this you have to wrought and cast. If you have additive manufacturing, so of course additively manufactured component will show inferior behavior in compared to wrought and cast. So you all please remember, among all the process, wrought product, which is rolled or forged product, will show the higher amount of fatigue limit, and cast is seen to be next, and additively manufactured component is seen to be further lower. So now you see most of the industry people are those who are working on additive manufacturing. They try to bring this value upper. Okay, there is a major challenge. Like you need to adopt heaping process, hot isostatic pressing, and you need to adopt some other post processing. By doing that, you can improve or you can move this curve towards higher. So this is a major area where you can focus if you are interested in and mechanical behavior of additively manufactured components. And similarly, you can see here. See, as I said, as built and HIP is hot isostatic processing. So people have attempted and they have seen that there is a quite significant improvement in the fatigue limit by adopting the HIP process. So next is fitting of a cracked specimen. So far what I discussed is corresponding to this specimen, which is a dog bone specimen. But for some of the industrial requirement, we need to actually test the component in presence of the crack. So basically how the component behaves under fatigue in presence of crack, whether the crack is stable, if stable, for how long it is stable, and once the crack is initiated, how long it will take for to reach the fracture. So if you take the failure, it includes crack initiation, crack propagation. So to find the crack initiation propagation, we need to use this sample. This is called actually sample with the notch. So most of the tests are done using mode 1. It's called crack opening mode, and basically what we do, we record the crack propagation rate. There is a dA by dN. A is the crack length, this is the crack length, and record the dA by dN with respect to del K. So here del K is the fracture toughness parameter. You can later fit this by using the Paris law, dA by dN equal to A, which is constant, to del K to the power P. So the P values generally it is approximately ranging 3 to 4. So once if you know this curve, or if you plot this curve, you find the dA by dN is straight line, then you use that, and you can actually further take these values to compare the other materials. Now this is how actually we print the component. This is called CTOD components. So once you see here, we printed components horizontally, vertically, and all those things, and we subject this component under fluctuating load, and we actually measure how the crack is propagating with respect to del K value. And very interestingly, you can see that the samples which are actually printed horizontally, it shows lesser amount of crack propagation, so which is quite interesting. And we also tested this component under various heat treatment conditions, surface hardened conditions, and we measured how the crack size is increasing with respect to number of cycles. So next testing is hardness testing, which is quite familiar, basically to find the impression dimensions. So if the material is softer, it will make a larger or deeper impression. If the material is hard, short and minimum deeper or minimum impressions will be made on the material. So there are actually several requirements. So if you work on tribology, you look for high hardness. High hardness is mostly desirable to reduce the plastic deformation and wear. If you actually work on machining, you prefer always for low hardness. If fracture mechanics, hard and brittle, it's a combination. This combination is what you look for. For metal forming, so you always look for low hardness. So it again depends the properties or the applications. So this can be determined by using. There are several hardness testing like Vickers, Brilnell, Knoop. Then you have annotations like that. So for example, if you take the Rockwell hardness, so this is a very standard and old method. So basically, you have indenter makes the pricks, and you find how much amount of depth has been actually penetrated in. So that's what actually determined by using the Rockwell hardness. So how much depth of impression is made by using this test is what determined, and that is shown in the C scale. So if the material is given with the 64 HRC, 64 is the highest hardness, HR Rockwell hardness in C scale. So you also have superficial. If the superficial technique is used, then you will be referring that with these numbers 81H or 30N. So this is how actually you refer the superficial. So there are several other techniques available. So the way you measure the resistance or scratch resistance or the resistance to the permanent deformation, they are different. And you can actually refer this slide for more details. And the next important property is the creep. So basically, some of the components what we manufacture by additive manufacturing is used in aerospace applications. When it comes to aerospace, high temperature is involved. So you need to know actually how the component behaves at high temperature. So in that case, we don't prefer to do high temperature tensile test. So high temperature tensile test, the test is completed in a very short time. So maybe in a few seconds, but these components are exposed at high temperature for longer time. So then we need to know how the material behaves under high temperature and high stress for longer time. So that's called time dependent deformation, right? So it is called a creep. So it is nothing but a time dependent deformation of material under the influence of combination of load and elevated temperature. So we can actually put this component under high temperature, normally greater than 0.3 of its melting point. So that's how most of the high temperature components experience. So by doing this, you can do creep test and also creep rupture test. Creep rupture test is slightly or relatively shorter test. So wherein you apply more amount of stress to make the component fracture in a shorter time. So that's called creep rupture test. So you see, this all actually industry requirement. So different materials will operate at a different temperature. Then you can fix or choose the temperature according to the applications. So why we are doing, because these materials will experience difficulties at higher temperature. As the moment you increase the temperature, there are several other problems. Strength decreases, so mobility of atoms increase, deformation is taking place at the grain boundary, recrystallization taking place, oxidation. These all actually problem. So all these things can be captured in creep data. So creep data will look like this. So basically strain rate versus the time, or strain versus time. You can also plot a strain rate versus time. So at a constant load, you have sample like a dog bone sample. You just apply the constant stress and heat the sample, or keep the environment higher temperature, and measure the strain with respect to temperature. It looks curved like this. So you have three regimes: regime 1, regime 2, regime 3. So basically primary, secondary, and tertiary creep regions. So this is done basically by using this kind of test setups. So like I said, there are three regimes. So mostly it is used, the second regime is called secondary in a creep regime for design. So you need to get this data. So this data is called creep data, d by dt, which is minimum creep rate. You use this data for the for your materials or for your applications. So there are actually several information given. I'm not going to detail about it. So what is important, like what you're saying is, see, at high temperature grain boundary sliding is taking place. So once the grain boundary sliding is taking place, it loses its collapse. I mean, structure would lead to the collapsing. So once the structure is collapsing, you can see it will progress, right? So the strain rate will increase, high d by dt, which is creep rate, will be increased quite significantly, and that can be mapped by using the creep map basically, right? So the creep map, that will give whether the creep is cobalt or dislocation, or a Nabarro herring or dislocation. So you can find basically what is the major mechanism of the creep, and where you can fit in this mechanism maps. So with this, I'm closing my lecture. Thank you. If you have any questions, I'll be happy to answer.
Yeah, thank you, Dr. Kesavan. It's actually informative and a wonderful session we had. Definitely it is going to be an eye-opener for those who are willing to pursue research in additive manufacturing. Thank you very much. Audience, if you want to have any clarification from Dr. Kesavan, you can ask. Rajesh, you raised your hand. Why don't you type in chat box? Rajesh?
Yeah, I got the question. So,
Yeah, yeah.
so where in IIT Palakkad, what kind of facilities available on research? See, at IIT Palakkad, I'll tell you. So we have started central facility for. Hello, am I audible to all of you?
Yeah, you are
Okay, so we have a central facility for materials and manufacturing engineering, wherein we house almost all the state-of-art equipments. One such equipment is 3D metal printer. So we have one 3D metal printer, which is a EOS M290 machine, which is imported from Germany. It is a very recent machine. We can use any kind of materials, and if you look at any other places, there they don't have option of varying parameters, laser parameters, or any other processing parameters. Whereas here we have all those controls. You can make components by varying or tweaking any parameters. Right, so there is one facilities we have. Apart from that, we also have micro manufacturing or micro manufacturing center. Then when it comes to materials characterization, we have SEM with EDS, EBSD, and almost all the material testing facilities we have. So tensile testing, fatigue testing, hardness testing, and what other testing facilities we have all. We don't have chemical testing of materials, but anything you name mechanical testing, we have. So going forward, we'll be adding a few more equipments. So like tribometers, and we are going to add so something like 6-axis milling machine and the X-ray CT machines and all those things. But we will not be adding them in a recent, but we will be adding maybe after 6 months or 1 year. So currently we have some basic setup to make 3D metal printing and test the 3D metal printed components. And we also have good amount of material characterization facility too. I think I answered the first one. Second, do we get all details of the material by manufacturers? Yeah, you can get. So I think this by Ilangavan and Madhavan. Yeah, you can get all the materials details. So I mean, if you want to print a component by using Ti6 for powder, so anyway, OEM, I mean, the person who is supplying the powder, he'll give you all the details. So apart from that, if you want to do tests, say for example, optical emission spectroscopy, you do that, and you can get the chemical composition of the details. You do further test, let's say laser scattering for finding its size distribution, shape distribution, all those things. Those things are possible. I think you can get that. Yeah, thermal properties of AM components compared with the ASCAST. So I don't have much information about it. To me, as long as this is a metallic component and the process is different. So of course the process, see, the thermal properties will be altered if you have some other actually constituents in it. For example, if the additively manufactured components have more amount of porous in it, then of course it will alter its thermal properties. So here we almost achieve 100% theoretical density. So wherein I expect, but I did not do any testing, I expect it should be almost the same as long as it is metal. We don't introduce any pores in it. Any other questions? I'm seeing only those questions.
Okay, if there is no more questions, let us wind up this session. Thank you, Kesavan, for the wonderful session.
Thank you, sir.
I thank all the audience, and reassemble 10 minutes before the next session. Okay.
Okay.
Feedback form is there
Thank
in the chat box. Yeah. Thank you, Kesavan.
Yes, sir.
Feedback form is there in the chat box. Fill it up.